Welcome to this video on enthalpy, and before we dive into some examples defining enthalpy, I want us to remember what I've written for you right here, the first law of thermodynamics, which is essentially just a statement of conservation of energy, which you probably learned way back in elementary school and definitely learned in middle school. And all the first law of thermodynamics says is that energy cannot be created or destroyed. And so when we look at the first law in the context of a chemical reaction, I've drawn for you here both in an equation form and in pictorial form, the combustion of methane. In any chemical reaction, the amount of energy on the left-hand side must equal the amount of energy on the right-hand side. We can't create energy to have more energy on this side. We can't just lose energy to the universe. We can't just take it out of the universe. That's not possible yet. So we can't have less energy on this side than we have on this side. There always has to be the same amount. And so let's think about that idea when we discuss in more detail the combustion of methane. And so this is how the combustion of methane works. We have one methane molecule, CH4, we add two oxygen molecules, two O2s, and we produce one carbon dioxide molecule and two water molecules. And now I'm going to tell you a few things about these different products and reactants. The first thing I'm going to tell you is that these products are more stable than the reactants. The reactants are less stable. What does stable really mean? When we talk about stability, we're just talking about stronger bonds. So in total, when we sum up the strength of methane bonds, the strength of oxygen gas bonds, when we compare them to the strength of carbon dioxide bonds and water bonds, these bonds are stronger. They have more energy. What does that really mean? Well, if we think about the energy that's available to the molecules, that's not bound up in bonds, there's less of that, what we might call free energy, over here, because it's all locked up in these really strong bonds. We've got really strong bonds, and it's tough to get at that energy. And so there's less free energy available on the right-hand side of the equation than there is on this side. More free energy. And that sort of sounds like a violation of the first law. I just told you that we've got to have the same amount of energy on the left-hand side as we do on the right-hand side. But here, even though there's more bond energy on this side, it looks like that in terms of free energy, energy that's not stored in bonds, there's more of that on the left-hand side. How does that work? How does this reaction actually take place? Well, if you think about what we know about the combustion of methane, we know that when combustion is essentially just fire, and fires tend to give off a lot of heat. And it's the same thing in this reaction. Whenever we combust, we add oxygen gas to methane and they react. In addition to carbon dioxide and water, we produce a heck of a lot of heat. And heat, we know, is just energy. It's just energy moving in the universe. And so maybe we could add a heat term to this reaction, to the product side of the reactions. Not only do we produce carbon dioxide and water, we also produce heat. And if we add that heat energy to the free energy of these products, that's going to equal exactly the free energy of the reactants. And so this way, we balance the energy on the right-hand side with the energy on the left-hand side. Let's look at another reaction, the formation of nitric oxide from nitrogen gas and oxygen gas. In this scenario, nitric oxide, NO, is less stable than its reactants. Its reactants are more stable. And just like we described up here, if something's less stable, it has more free energy. There's more energy not bound up in bonds than there is on the reactant side, less free energy. The reason I'm putting free in quotation marks is that we're actually going to discuss a topic known as free energy in a much later video, but I just use the term free here to differentiate between the energy stored in bonds and the energy available to the system. There's more on the left-hand side, or excuse me, there's more on the right-hand side than there is on the left-hand side. So again, it looks like we've got a contradiction. How can the first law of thermodynamics, which says that we can't we can't create or destroy energy, how do we reconcile that with this kind of reaction where there's more energy? It looks like there's more energy on the right-hand side. Well, just like we did up here when we added heat to the product side to balance the energy of the chemical reaction, over here we're going to add heat to the left-hand side. Heat plus nitrogen gas and oxygen gas. And in this way, again, I've repeated myself multiple times, but I want to hammer home this concept. By adding this heat term to either side of the reaction, what we're doing is we're making sure these reactions obey the first law of thermodynamics. And so we can see that reactions can either produce heat as a product, or they can consume heat as a reactant. And you may have heard these terms before, but we characterize any reaction that releases heat as exothermic, and you can remember that because exo is a general sort of prefix rather that means release or out of, and reactions that absorb heat are endothermic. Endotherms are warm-blooded animals, but in this case they're animals which absorb heat, or which they're reactions which absorb heat. Endo means coming into. And something to keep in mind when we discuss exothermic and endothermic reactions, we need to differentiate between something called the system and something called the surroundings. The system, so here I've got a little aqueous solution with some chemical in sort of an orangey color. The system is actually the chemicals which we're talking about. So the system would be these orange things. This would be the system. The surroundings is everything around the system. Everything around the system. When we talk about energy flow, so something being exothermic or endothermic, we're referring to the system itself. So heat changes are defined with respect to WRT, with respect to the system. So when we say something is exothermic, it's releasing heat from the system to the surroundings. So the surroundings are going to heat up. Conversely, if we have an endothermic reaction that consumes heat, it's the system consuming heat and the surroundings losing heat, getting colder. And so if we want to think about what happens to the surroundings with any kind of chemical reaction, we flip what happens to the system. So if the system loses energy, the surroundings gain energy. If the system gains energy, the surroundings lose energy. That's just sort of a little clarification to keep in mind. And now we're ready to define enthalpy. And so enthalpy is sort of a thermodynamic concept which in its sort of pure form is equal to energy plus the product of pressure times volume. And so we can say that the change in enthalpy, H is the term we use for enthalpy, so this is enthalpy for H, is equal to the change in energy times the change in pressure times volume. And we can get a few things out of this little equation. The first thing we can say, I'm going to switch to a green color, is that at constant pressure, constant P, the enthalpy change of a reaction, so the amount by which the enthalpy changes, is equal to the amount by which energy changes. And now we see why we can use enthalpy to describe chemical reactions. Almost all chemical reactions, like we do in the lab, like we do on tests and exams, occur at constant pressure. That means when we describe the enthalpy change of a reaction, we're describing how the energy of that reaction, how the energy of this system changes. And so when you hear chemists talk about enthalpy change, or you see it in a problem, you should just think, oh, that's the same thing as the heat flow in a reaction. So for our purposes, an enthalpy change is just the change in heat. And up here we described heat in terms of exothermic and endothermic reactions, and we quantify that using enthalpy changes. In reality, enthalpy is a little more complicated because we have this PV term, and so if pressure changes or volume changes, or pressure changes and volume changes, enthalpy change is not just equal to the energy change, but for our purposes, we can say that they're pretty much equivalent. And so when we see exothermic and endothermic reactions, we're often going to see these little delta H's. And these delta H's, again, are just referring to enthalpy changes. And enthalpy changes, again, just quantify the amount of energy and heat produced in a chemical reaction. And so this would indicate that 180 kilojoules of energy is absorbed. So the system gains 180 kilojoules of energy. So system gains energy. System gains energy. Over here, the enthalpy change is negative, and so the system loses energy. System loses energy. And we know that whenever we have a change in something, so if we have an enthalpy change, that's just defining the difference in the enthalpy of products minus enthalpy of reactants. That's what change is. So if delta H is positive, it means the products have more energy, more free energy. That's like what happened up here with the production of a less stable substance which has more free energy. There's more enthalpy on the product side than there is on the reactant side. And so then we need to add energy to the left-hand side to make that reaction go. So that reaction is endothermic. So if delta H is positive, reaction is endothermic, and the products have more free energy. And then you might be able to figure out what happens if the enthalpy change is negative. If that happens, we're releasing energy to the system, which means these products have less energy and less free energy than the reactants, and so the energy, or rather the reaction, can be defined as exothermic. And so enthalpy changes, these delta H's, you're probably going to see them in a lot of different chemical equations, are really just a measure of how much energy the system, so that the chemicals, the products themselves, lose or gain in the process of a chemical reaction. And also that this number, this enthalpy change, describes the relative amount of free energy we have on both sides of a chemical reaction. I'll see you in the next video.